First, maybe we could quickly introduce ourselves. I'm Talia Kalfa. I have a background in architecture and I'm now doing my second master's in building technology at TU Delft. And I'm your moderator for this MOOC. I'm the one answering your questions and uploading the material in the platform. So, hi.
Maybe we
Alessandra.
introduce each other too.
Yes, Alessandra and Miriam.
Yeah, so I'm Alessandra Navarro. I'm an assistant professor at UDEFT. I work daily with Talia, not only on this MOOC, but in other facade-related courses. And I'm here with Miriam Schuster.
Yes, so hi again, everyone. My name is Miriam Schuster. I'm from TU Darmstadt. I'm a postdoctoral researcher and I'm a civil engineer. That's my background. And yeah, I'm working at the Structural Mechanics Institute.
Okay. Now we'll share my screen.
Maybe just a forward. So this is the first of our interactive sessions. I believe that tomorrow you're going to start the next module, which is on thermal, right, Talia? Hasn't started yet. So we mainly focus to the discussion on the structural part, which is the week you are completing or you were supposed to complete by tomorrow. But of course, it's also you have time within these weeks to complete the modules. Yes, Talia, please continue. Sorry to interrupt.
No, of course. Today we will go over some updates that we did in the table of deflection and the caseloads, and of course go over some of the assignments and the examples because some of you completed and uploaded your answers. And of course, throughout this webinar, feel free to upload your question to the Zoom chat or ask your questions freely. First, we'll go over the table and Miriam will help us with the explanation, our expert.
So maybe to introduce, I think one of you, Matteo, if I'm not wrong, flagged that there was a mistake in the platform, which it was true. There was a visualization problems and the figures were not matched with the right equation. It was a platform issue when we built the page. So thanks for flagging this. Yes, we have reported the right combination of equations and schemes, structural schemes. I don't know, Miriam, if you want to do an overarching comment.
Yes, so maybe I just comment the table very briefly. So we have here two different structural systems. On the one hand, we have the single supported beam, and on the other hand, we have a cantilever. So yeah, so the left-hand side is the single supported beam, right-hand side is the cantilever. And we have here different load cases, and these represent the loads which are mainly appearing in facades, which are mainly wind, which is here shown as a uniformly distributed load, the W, and we have single loads, which are shown here by P. And as you see, the maximum deflection is always dependent on that load, on the span, and also on the material, which is here described by the Young's modulus, and the geometry, which is described by the I.
Great, thank you, Miriam.
I don't know if there is any question on this part of the update. Okay, all clear. We already updated the edX platform, so that is corrected now. So you will find now in the system the right equations, combination of equations, load and support scheme. But of course, we are always here if you see if you have other questions also later on. Okay. Thanks.
Then we'll go over the first assignment you had to complete. So before we dive into the assignments, let's take a moment to look at what the structural design principles mean in the concept of facades. At this stage of the course, the focus is more on understanding facades not just as architectural surfaces, but as systems that have to deal with wind, gravity, and building movement. So in this module, we look into these forces that travel through mullions, transoms, and their connections, and how the geometry of the grid, for example, influences stiffness and overall performance. And this foundation is the one that will help you make sense of the examples that we show you. And now we'll review the steps you'll follow in your assignments using some examples of your peers. We will look into two examples, and this is the first one. Here, in step one, basically what you have to do is to pick a facade and then identify the important elements to later identify the load path. So in this example, your peer identified clearly a facade. The type of a facade is correctly mentioned as a stick curtain wall, and the mullions and transoms are nicely labeled. A small improvement, for example, for this assignment would be to also mention which is this building, and maybe annotate the image a bit more to highlight these elements that are important and crucial for the load paths. Then we look at the second step, where you have to create a small sketch, identify again, annotate the facade that you've chosen, and identify these elements, crucial elements, while also sketching the paths and the loads and types that are acting on the facade. This student did exactly what we were looking for. It's a very good example. It's a clear sketch of the facade base, showing how the load and wind load act on the system. You can see here the identification of the frame, self-weight, the glass load acting on the transoms, and the wind pressure applied across the panels. He also showed the load arrows very clearly, which is great. The key learning of step 2 is simply to show the existing load path, not to calculate anything yet, but to recognize how the loads move through a typical stick curtain wall for this example. A tiny improvement would be, for example, that applies to other submissions, and you can think about it at your own time when you also do the assignment, is how this part would be connected to the main structure, for example, through the mullions, brackets, back to the slab or beam. But overall, the step was complete and really well. This is exactly the level that we're looking for step 2. Then if we have a look at step 3, here we have to you have to propose a modification and then reassign the basic geometric values and do the calculations before and after. Here we see that your peer added a transom in the middle of the second part of the facade. However, it would be more helpful to see to add the actual numbers of the new geometric values and continue with the calculations. Here we've added the calculations as an example, for the tributary area, the resulting load on the transom, and the shear force. And of course, we would normally continue in the same way for the bending moment, the transom, and the deflection, and the required sectional properties, as you read in module 2, the module that we uploaded. But in conclusion, and to sum up the main idea, by adding the extra transom in this example, you effectively have the tributary height, which means that the load per transom, the shear and the bending all drop significantly. And when we use the beam formulas, we clearly see that the Vmax becomes half, and then the deflection, for example, becomes only 0.025 if you do the calculations of the original. And this means that the transom can be much lighter and stiffer because it now carries less load and over a shorter span, while the moment in the mullions stay almost unchanged. And these are the conclusions we want you to draw. That's why we want you to do the calculations for the before and after. And finally, in step 4, you have to complete the sentences using your example and your modifications, which your peer did very well here. And also redraw the main diagrams for the modifications. This is very nice work, and the reasoning about the mullion is correct, since the span and support conditions don't change. It's reasonable that the diagrams for the mullions remain almost the same for before and after the modification. Maybe some small addition here would be the effect on the transom, which is actually where the design and the modification change has the biggest impact. And as we mentioned, by adding the extra transom, you have the tributary height. So maybe it would be great if here we could add a second set of diagrams or even a simple sketch for the transom showing smaller bending and shear peaks after the change. That will make step 4 more complete. But again, maybe for this assignment, this is enough. And then we'll look into a second example of your peers, which is a bit different and very interesting. Here again, for step 1, the example is really nicely done. You see the facade is clearly identified. We even get a sketch showing the main elements, and the student correctly describes the system as a stick curtain wall with vertical still mullions and horizontal transoms. And in the annotated sketch on the right makes it very easy to see how the system works. Then if we go to step 2, again, we see in detail that the student clearly separates wind pressure from gravity load and explains exactly how each type of load moves through the facade, and specifically from the glass to the transom, then into the mullion, and finally into the building structure. You can see in the sketches on the right and also in the discussion forum that the load paths are very easy to understand here. They're step by step. The only small improvement would be to explicitly show or mention where the loads finally go into the primary structure, again, as an addition. But overall, this is an excellent step 2 submission. And here we see a full step 3. We see the student clearly shows the geometric modification, which is basically doubling the mullion height. And they have also identified the new geometric values, the before and after. And they correctly analyze how these changes affect the behavior of the facade. They correctly identify that the tributary width stays the same and the wind pressure doesn't change, but what changes is the bending and deflection of the mullion because of the taller span. Now, one interesting point that I would like to mention in this step, this came from another student in the forum discussion, and I would like to mention it briefly because it's very interesting. Your peer talked about the connection and how the connections affect the load paths and the bending. When we talk about increased bending in the mullion, where the bending actually goes depends on the connection type at the structure. If the mullion is welded to a base plate and fixed rigidly with anchors, then yes, the end fixings will experience higher moment. But if the facade is connected with typical pin type bracket connection, for example, which allows rotation, then the bracket does not carry bending moment. And in that case, any moment at the anchor would only come from geometric eccentricity between the through bolt and the anchors, not from the Mallian bending itself. Here the student's analysis for the example is correct for the member behavior, but the comment also is very interesting and correct in pointing out how the connection detail actually determines how much of the bending is actually transmitted to the primary structure. This is a great example of how facade engineering is always a combination of member behavior and connection behavior. However, you don't have to analyze the type of connections for these submissions, and you don't have to go into details if you don't want to. And lastly, here you see clearly done the matches that the submission form matches the intent of the exercise. The student correctly recognizes that when the Mallian height doubles, the bending and deflection increase, and the member may need to be thicker or stiffer. The gram you can see on the diagrams on the right that they show the before and after behavior with higher bending moments and a steeper shear line after the modification. So to summarize about the assessment of the assignment, we are not looking for perfect drawings or super precise numbers. We're looking for clear load paths, a sensible geometric change, and a logical link between span and bending and deflection. If you follow all 4 steps and justify your reasoning, you're absolutely on the right track. And if you realize now that while you're working on the assignment, you've missed, for example, a small calculation or a comparison diagram, feel free to, again, re-upload your changes, and we will be happy to assess your changes and your questions. Of course, keep asking questions in the forum, like some of you already did, Matteo, with the beam formulas. Because that's how you actually learn. We really encourage you to submit your assignments, even if it feels imperfect. The goal is for you to actually practice the process and get feedback. That's where the learning again happens. And please keep asking questions, even if questions occur in every step of the assignment. We'll be following up with everyone. So of course, don't hesitate to reach out.
We already have a question in the chat right now, which was from also need to check buckling if we increase the Mallian height. And yes, that's absolutely right. Of course, buckling is very dependent on the buckling length. And since we are increasing this length, then we should also recheck the buckling.
So now we would like to open the floor to you. Are there any questions or any more questions that came up?
Curiosity, point of discussion. We can leave a moment for getting your questions.
We can take some time.
Yes, please, you can just speak out if you want.
Okay. So for me, the question is about determining the shape of the tributary area. I'm following the example of the step 2 in module 2.6, and I'm trying to understand how we decide how the trip area is split out. I don't know if you guys have some additional examples to show how to split it up, but this is a point that's a bit unclear for me.
So maybe I can try to answer this. So when we have a transom mullion facade, then we say that all the horizontal loads coming from wind are carried by the mullions, so the vertical parts. And we say, okay, we multiply the surface load by half of the width of the window on the right side plus half of the width of the window on the left-hand side of those margins.
Oh, okay. I can't share my screen, so it's hard to explain. Hard to explain my question. It's okay.
We cannot. Can we allow to share the screen, Talia? Right now, sorry, you're muted, Talia.
It should be allowed. And now I stop sharing my screen. Can you try it again?
Yeah, I'll try now. Okay, so this is my question essentially. So following this example, girder 1, it's getting the point loads from the secondary beams. That is clear to me. Girder 2, it is getting some of the point load from this primary beam as well as some distributed load from this surface area. My question is, for instance, why in girder 1 isn't it taking some distributed load from the area? Basically, why do these diagrams look different in terms of how the area is split up? I don't know if that makes any sense. Structural engineering isn't my background, so I'm struggling a little bit.
So I'm just reading again the examples. So 1 minute, please. Okay, so here it really depends a bit on the loaf part. So when we are looking at the windows, for example, or the infill elements, then they have one span direction, which means that for the top example, we see that the surface load would go to the horizontal elements at first. You see this the arrows on the window which tell us in which direction the load is going. So they are first going on this horizontal element, and this horizontal element is connected to the vertical one. So at this point of intersection, we have a single load then.
Oh, I see. Go in the horizontal direction just because that's shorter, so it's more
Yes,
tilted.
exactly. It's shorter, and yeah, so that's what the arrows are showing. This is the load part. So we have a distributed load on the horizontal parts, and then they are transferred to the vertical parts as a single load.
Okay. No, that's helpful. Thank you.
You're welcome.
Are there any more questions?
Yeah, I have a question regarding more like the terminology because we're using Mullion and Transom, and I've found my example, which is like the Rotterdam Central train station, and it's quite like not weird, but like the main load-bearing structure of the entire glass facade. Maybe I can share an image in the chat. Is like having these huge beams, but are the transom, if I understand correctly. Wait, I can.
It might be that it's a facade with a different system that is not transom and Mullion. But if you share a picture, we can have a brief look.
Can I put a picture in the chat? No.
You can put the link of a picture.
Do I have a link?
Also share the screen.
Or
otherwise
share
maybe-
your screen.
Yeah.
That's
Yes,
maybe
of
the
course.
easiest
Oh
way.
yeah, I can share my screen would be, I guess, the easiest.
There's a green button which you can use.
Yep, found it. And I think you can see here now my screen.
Mm-hmm.
Yes.
And so this is the facade. So it has these glass panels that are attached to transom. And these transom are then bolted to these beams that spans through the entire facade. So I assume they are the mullions. And then it goes directly to the it goes directly to the ground, basically. So I don't know. I don't know if I should call them mullion and transom, and how should I depict them as the main load-bearing facade or like the main facade of the main bearing facade part of the facade, and then there is something else for the load-bearing facade because it's quite kind of different from the examples you showed earlier. So I'm not sure how to depict and then also like explain a bit load path would be easy. It's like transom and then it goes to these rigid beams and they have shape to the shape of like the wind transfer, but I don't think it's like millions, or maybe, I don't know.
I would say it depends a bit on how the main structure of the building is supported, but to me it looks like these are mullions. They are huge, but it's okay because they have a very long height. So they need to be more massive than the case where we from floor to floor, for example. But this is also possible, and for me it's a standard transom mullion facade system. Yes. Alessandra, what would you say?
I agree, but I have a question that we don't know with this picture. The same question you have, like if it's a primary structure, if these mullions are also primary structure, it's difficult to see effectively. It could be, but it seems to me that there is a clear hierarchy between the horizontal thinner transoms and the vertical mullions that are definitely supporting these horizontal transoms. So in overarching terms, it's the same hierarchy.
Yep.
Then, of course, we don't know if this. But plus, it's very nice. It seems from the picture that they are shaped to increase the section in the middle because of buckling, probably.
Yeah, or
Or
maybe
no, just
moment,
because of the pressure, the distributed.
maybe. I've assumed in my assignment it would be this, and that's why I took this example because it was nice to show that we can reduce some of the thickness on different level depending on the loads or moment. But yeah, then I thought maybe it's load bearing for the entire roof, and I was like, oh,
Yeah, that's what we can't really detect from the pictures. But the load transfer is mainly the same. So maybe we have additional loads from the roof itself. But at least when we are looking for the wind loads, for example, then the load path is exactly the same then for the examples that we showed before.
okay, perfect. Thank you.
Nice example indeed. Any other question in relation to structures in facades in general? Now that we're gonna conclude this first topic.
If we have the time, I have another question. Okay.
Yes, sure.
I will share my screen. So I was originally going to do my assignment on a storefront, and so pretty standard storefront. So we have the transoms and then we have the mullions. It's almost like on one side, it's almost like a punch window. So the mullion is attached into the structure using some fasteners. I will assume at least one of these fasteners are slotted, so it's so it allows for some movement. The confusing thing for me is the transom. For me, the self weight of the glass is the weight of the glass is going into the transom, and there are two fasteners here, and it's put on a shim pack, so it's sitting on the ground. So to me, the full weight of the gravity load of the glass is going into the transom. But it's also because these are the 2 points where it's resting on the ground. It's almost like it's two pin structures, or two pinned supports, and that's kind of where I'm struggling, because it's not supported on the ends like all of the examples we've done, but it's kind of supported in two spots in the middle.
Do you have a picture of the real system?
I do. Courses. It's actually the same one that I'll share first a picture of the details. This is actually a project that I did before for a circularity course with TU Delft. So this is the bottom transom, and it is bolted to the ground in between. So that's where I'm struggling, just how to define this. And this is the mullion, very similar to the bottom transom, and again, it's bolted to a wall. And I'm
But this is not a mullion. It's not a curtain wall system. It seems to me it's just a window punch window system.
Yeah, fair enough.
So do you have a whole picture of the system, or because for the details I see, it doesn't. I don't know, Mia, what do you think? It doesn't seem to me. Okay, here would be different. This is different.
No, I'll find the right picture. I'll find the right picture.
Okay.
I'm just going.
That was a glass facade, yes. But this to me.
Yeah, also for the lowest, always the question, is it linearly supported maybe over the whole length? So even when you only have two fixing points, it can be that you have this full linear support.
Yeah.
Right, because the fixed points are just how the frame would offload the loads to the main structure.
To the main structure, yeah. Okay.
But it does. Maybe it's not a system with a grid primary and secondary structure. Yes, in fact, I was thinking it seems to me like a ground floor facade.
It is, yeah.
Yeah, so in this case, you have the dead load of the glass, which is directly going to the ground, to the foundation. Yes, you don't really have this.
But do we say it's
typical
would you say it's like a simply supported beam, where I don't know, you have like I don't remember in English the word, sorry, I remember in Italian. You have a hinge on the ground and just the simple support, the one with the wheels.
Yes, for the mullion, I would say so. So we have a pin roller at the bottom and at the very top. So that's your simply supported beam, which you can use for your wind load transfer. And then you have your horizontal loads, which are going to the roof and to the foundation directly. And yeah, the dead load of the glass is directly introduced to the primary structure, which is in the ground here. Yeah.
I can pick a more traditional example. I just already have these pictures.
That's nice because it's a common structure that you see everywhere.
You could, for example, when you're using that one, you could modify this facade in the step where you are asked to modify it if by introducing transoms in the middle of the facade, for example.
Yeah, that's a good point. Because then you would halve the wind pressure, but you will also halve the dead loads.
Self-weight of the glass over a
Yes.
small section.
Yes.
Okay. No, that'd be interesting. Thank you.
Yeah, often you see ground floors that are more stick systems too. But this doesn't seem to me a stick system. It seems to me traditional window, let's say large window system. Nice to see all this variety of examples. If there are not other questions, we would wrap up here. Last call for questions. Nice. So thank you for joining. Makes it very important. It's very important for us if you all join these sessions. It's a way for us to get feedback, but also to make sure your educational experience during this MOOC is as good as possible. So we will have another session like this towards the end, after you've completed the bigger parts of the physics part. From tomorrow we start with thermal energy. Then we will move to daylight and let's say the trade-off between solar radiation and visual comfort, and then do multi-domain comfort and acoustic. So looking forward to the next session then. And thank you very much, especially to Miriam and Talia to joining and helping today.
Thank you very much.
Thank you.
And we would like to inform you that, again, the webinar was recorded, so we will upload it to edX and you will be able to rewatch it at your own time again.
Thank you. Goodbye.
Thanks for your time. Cheers. Bye-bye.
Thank you. Bye.
Thank you.
Yes.